where we ended last time, let me mention a couple things that are coming up. So first, problem set 1. Is due in lab next week. And the way that's going to be graded, so you should write it all out. So funny. Okay. Due in lab next week. The way I'm going to grade it is you're going to do all your work, bring it in, and then one by one during lab, I'm going to pull you back into the back room, have you just sort of explain what you did. You know, I'll just ask you to kind of walk through your steps. And if I see anything that needs to be corrected or whatever, I can tell you, like, I'd like to see you do this. I'd like to see you do this. And then based on that discussion, and then so I can ask you to clarify things if something isn't that clear to me or whatever. Most of the time it goes pretty fast, and if your work makes sense, it's it goes really quickly. It takes a little longer if you go off on the wrong track or whatever, then we have to talk about it a little more. But it's graded out of 3. Most people who do it, and like, I guess I would say anybody who gives what I would call a good effort at it will get a 2, a 2.5, or a 3. Anything below 2.5 just kind of means you didn't spend enough time on it. Yep.
Is there, how many more problems are there going to be this semester?
How many weeks are left?
Like
6, 7?
I would say like 5. I don't know. Let me check.
Somewhere between 5 and 7?
Let me get back to you.
I'd say 3 more after this.
3 more?
Yeah,
Okay.
that's what I would guess. We can do them a little faster this semester because there aren't as many people in lab. You know, last year, like in lab, it would take multiple weeks to get through everybody.
Oh, we have 1 the week of finals, yeah.
Oh, yeah. Yeah, okay, so let's say 2 more and then 1 that you'll hand in like the week of finals.
Okay, I just wanted to know, like, so.
Right.
Like, I don't want 1 to be like the whole percent. I just wanted to make sure.
Yeah, yeah, yeah.
Okay.
Anybody, I guess the people who weren't in my class last semester have questions about the format? I mean, it seems like people always come to the first one really nervous because it's like an unusual way to do it, but it's pretty painless, I think, you know. Yep. Yeah, that's what I'd like to see, yeah. I'd like to see all your steps. And on these problem sets, on exams, if there's just a number wrong or something, it looks like it's clear to me that you just made a calculation mistake. I never take off points for that. On a problem set that you have a week to work on, I'm a little more picky about getting the right answer. I mean, sometimes I'll give full credit if you have the wrong answer, but you have extra time to check your work, so it seems reasonable to do the right method and get the right answer. It definitely helps to, I mean, at the very least, to, after you finish working on it, compare notes with someone else, make sure you had the same answer as them and that kind of stuff. I mean, that can help a lot. I would definitely recommend talking to someone about it. Somebody in the night class last night asked if I would put up a discussion thread, so I'll put that up today on D2L, so you can ask questions on that. Although it's sort of hard to, like in email or whatever, to ask questions about mathy stuff because you can't write the equations and stuff, but I'll put it up there. Any questions about the problem set? Any questions about, so has everybody started looking at it? If you have not, better start. Yep. Uh-huh. It's hard. I mean, these problem sets, yeah, they're hard. And like, I think they're considerably harder than the practice problems, you know. The idea is that you sort of, I mean, my plan is that you sort of drill the concepts into your head with the practice problems, and then come back to them, and you have to think a little more creatively about the problem sets. That's the way I design them. I think the way it usually works is the people who understand the stuff the best can do it by themselves, and I'd say half the class, maybe as much as half the class, would have a hard time doing it by themselves, and that's where, you know, working with other people helps.
Last question, like, I don't know, do we need to know about nitrogen in that question? I don't know if that's.
Oh yeah. So there's a
Because nitrogen is not given and no masses for it, that's given.
yeah,
And I was confused, like,
right.
I was trying to work on it.
Okay, so basically you have like a little bit of water. You have a known volume. All the rest is full of, and you don't even have to use nitrogen. You can use air, because online you can look up the specific heat of air. So you don't have to approximate it as nitrogen and oxygen and stuff. That would be a nuisance. Just use C, air. And all of the steps in this, it's sort of a calorimetry problem. All of the steps are going to take place in a constant volume. So you should use, when you're talking about the specific heat of gases, you should use the constant volume specific heat. But yeah, so anything that's not given, I mean, you can just Google that stuff into, you know, type that stuff into Google, specific heat of air, specific heat of water, of steam, and those answers will pop right up for you. One of the guys in our department yesterday was showing the class like how Google will do conversions for you, and he started to type in 5 grams to kilograms, like to do a conversion, and he typed in 5 grams, and it auto-filled 5 grams of weed. Did you know you can use Google as a calculator? Like if you type in, if you type in 59 over 4, you know, squared or whatever, like it'll pop the answer up for you. It's cool. Yeah, it'll even do matrix and vector calculations and stuff. Yeah. Okay, so be sure when you're looking for the specific heats of gases, use the constant volume specific heats. Those are the ones that'll be labeled CV. Any other questions about the problem? Okay, and then exam 3 is coming up in not too long. That is, yeah, 2 weeks from today. Thursday, April 10th for you guys, and then for the night class, Wednesday, April 9th. So I guess probably next week I'll be able to tell you exactly what topics are going to be on it. Definitely thermodynamics, and definitely electric fields and electric potential. That's one set of practice problems, so you should be able to do all that stuff now, or after today. I'm going to start with a little of that stuff. Any other questions about anything with the class? Okay. So I'm just going to talk a little bit about capacitance and capacitors capacitors are a way to store charge and generate currents and an electric current. That's the main thing we're going to talk about in the next section. But a current is motion of charged particles. You can think of it as sort of an alternative to batteries. In a lot of ways, they do the same thing that batteries do. But compared to batteries, capacitors are useful for producing higher currents for shorter times. Shorter time intervals. And as kind of an explanation or a kind of a illustration of that, so a car battery that you pay $100 for or whatever only has a voltage of 12 volts. A 9-volt battery, that has a voltage of 9 volts. You could wire one up next to each other, put the positive of one onto the negative of the other one, and treat that, you could wrap it in duct tape and treat it like a single battery, and that would have 18 volts. So 2 9-volt batteries cost $2 or something. So what is it about a car battery that has, a lower voltage than these 2 9-volt batteries that makes it worth 50 times more or whatever, 100 times more? And why is a car battery huge? And like, oh, well, I'll just wire 2 9-volt batteries up to my car and that saves some money, Like that won't work. You'll be surprised to know. But why won't it work? It's because 18 volts is plenty of voltage to power your car, to start your car. But that 18 volts has to be used to produce a ton of electric current, the motion of a ton of charge. And 2 9-volt batteries just can't hold enough charge at one time to produce the current you need to start your car battery, to start your car. So that's what, like a car battery, it's so huge because it has the ability to generate a lot of current. And that's why it's so expensive. So it's not the voltage, and it's not like the car battery is 50,000 volts or something. It's just that it can produce those 12 volts while generating a lot of electric current, while transferring a lot of charge. That same kind of thing is what a capacitor is good for. So a capacitor doesn't have that problem of not having charge on hand. Once a capacitor is charged up to a certain voltage, it can discharge all of that charge as fast as you want it to. And so in applications where you need a really big electric current over a short time, capacitors are the way to go a lot of times. Here's what a capacitor looks like. You have one plate that's positively charged parallel to another plate that's negatively charged. You can see the similarity between what a capacitor looks like and those parallel plates that we've done calculations with. There's some small distance between them, and in fact, the smaller you can make that distance, the better the capacitor is. And the small gap of width d has to be filled with an insulator. Usually that insulator could be air, but usually it's some kind of dielectric material, it's called. It's just something that can be a dielectric material is just something that's an insulator even at a very small thickness, so that you can get these two plates really close together without the. So why do you have to have an insulator between them? Well, if you had a conductor between them, like, hey, maybe this is a better way to make a capacitor. Put a copper wire from here to here, you know? Maybe that would work better. Well, what would happen is, because of the attraction of the positive and negative sides, all of the electrons on the negative side would just move across the wire over to the positive side until they both had the same charge. And then nothing else would happen. You wouldn't have any charge stored. So the only reason you can store these charges is because no charge can move from one side to the other side. Okay? They really want to get over there, but they can't. And so what happens then is, if you have a copper wire here and a copper wire here, which is, how they're usually sold, then you hook this one up to something that requires electric power, light bulb, okay? Hook this one up over here, and all of a sudden, these charges that really want to get together, there's a really strong electric field that says the electrons in the negative side want to get over to the positive side. Now they have a path, and so they all go pouring through the wire, through the light bulb, light it up to get over here. The electrons on the negative side want to get to the positive side. So when they're given a path through a device, they travel through the device and power it. In a schematic diagram, understanding electric schematic diagrams is going to be like a big sort of subplot in all this electricity stuff. You represent them like either like this. So this is a battery, and this is a capacitor. Or sometimes you see it like this. So that's a battery again. Sometimes the capacitor is written as a line and then a curved line. I'm going to use just the two parallel lines. To charge a capacitor, oh, and so these schematic diagrams, these are the two circuit elements. So this is the capacitor, this is the battery. Yep.
When you finish your statement, I have a question about path of electrons versus path of electricity.
Yes. Okay, yeah. Yeah, that can be a super confusing thing. Well, so in these schematics, you have devices. In this case, we have a capacitor and a battery, and then you have wires. And so anything that isn't a device is just showing that there's a connection between this device and this device. One thing you should, okay, so let me erase this for a second. So notice, or let's say, one important thing to remember about schematics any 2 points on a schematic diagram that can be reached without passing through an element and the elements that we're going to talk about are batteries, capacitors, and resistors. Those haven't come up yet. So any 2 points where you can get from one to the other one without going through a circuit element have the same electric potential. If they have the same electric potential, then what's the potential difference between those 2 points? So if they each have an electric potential of 50, then the difference is 50 minus 50. So therefore they have an electric potential, and electric potential, remember, is voltage, of 0. And so if this represents like a battery connected to a wire connected to a capacitor, this battery could be 1,000 volts. You know, you could have batteries strung up across the room. 1,000 volts, this could be a big capacitor. If the wire you're using really has no resistance in it, like it really allows electricity to flow freely, you could go, now there's a lot of electricity flowing through that thing. An amount of electricity that if it went through your chest, it would liquefy you, you know. But you could go up to that, grab it, bite it, lick it, whatever, and none of that electricity would go through you, because the only way you get electricity to go through an element is to have a voltage across the two sides. So if you, okay, so if you went up to this, okay, so what's the voltage between this point and this point? 0. And so if I held it like this, there's 0 voltage across my hands, and that means that no current is going to go through my body, even though tons and tons of current could be flowing through this wire. Although, here's the thing, if this battery was 1,000 volts, and you put one hand on this side and one hand on the other side, the 1,000-volt battery means that there's a potential difference of 1,000 volts on the two sides. So if you did that, you'd be in bad shape, you know, because your one hand, the potential difference between your two hands would be 1,000 volts, and that would send a lot of current through your body. Okay, well, we'll get back to those ideas. Yes. So current is the actual motion of the charged particles, and electrons are always the charged particles that are moving. Voltage describes the electric field that makes those charged particles move. Okay, so the voltage determines how much charges want to get from one place to the other. The current is the actual motion of those charges from one place to the other. Okay, current is what charges electrical devices and injures people and stuff. Voltage is what makes those charges move. So think of voltage as kind of the engine that pushes these charged particles around. Okay. Okay, question?
When we talked about current, we talked about, I guess it just seems opposite to me because we're talking about electrons, which we have.
Right.
Electrons
Yeah.
are negative, so they have to go to positive, but current seems to
Right.
be directionally applied in the opposite way.
Yeah. Okay, so this is something, I never really know how to talk about this because I think some people, so there is like a disconnect there. You're right, that's a real thing. If it doesn't ever occur to you or bother you, then mentioning it, I think, is only confusing to people. But for the people who it occurs to, like, it's good to address. So let me just, yeah. I mean, for a lot of people, it's going to come up at some point as they're thinking about this stuff, like, wait a second, this doesn't make any sense. So, okay, in case this bothers you, so, you know, store this away for future reference. We define current direction as the motion of positive charge but electric current actually comes from the motion of electrons. And since those are negative particles, so it actually comes from the motion of electrons which are negative. Okay, so what that means is what we call a positive current is actually opposite the direction that objects are moving. Okay, but if you think about, this sort of came up in talking about induced current. If an electron goes from here to here, as this electron moves this way, a net positive charge moves this way. That net positive charge, it's not an actual object. It's just like the void left by this electron. You know, it makes this side less negative, so it makes it more positive. Okay, and so current, what we call the current direction, is actually opposite the direction the particles, the electrons, move. Okay, so when you think about current, the way to think about it is thinking about like a positive charge moving one direction. That's how to think about current. It just, you might want to sort of in the back of your mind remember that what's really causing it is the motion of electrons in the other direction. Okay, so it's like what we're really following with current is the motion of gaps left by electrons. I just have to think about the sign. I mean, that loosely, like, yes, something like that is what's going on, yeah. If you take, so like if you have 5 coulombs here and 5 coulombs here, and you take a charge of -1 coulomb and move it over here, right, from here to here, now you have +5 coulombs on this side, +4 coulombs on this side. And so mathematically, it's just as if you took a positive charge and moved it this way, even though what you really did was take a negative charge and move it this way. Do you know what I mean? So that's something that, like, I don't know, maybe that's something to, you can ask me about it later if it starts to confuse you. But so why would it be that way? Like, it's so confusing. The reason it's that way is because people were doing electrical calculations a long time before they knew what electrons and protons were. And so, and I believe, my understanding is that actually Benjamin Franklin is largely responsible for the sign convention, so it's his fault. But, you know, then, so they did all these definitions of how to do calculations, and then after those were entrenched, everybody had been using them for decades or possibly centuries. I don't know when they started doing those calculations. I guess centuries, a couple centuries. Then they figured out that what's really moving are these negative charges, and then they were sort of stuck. They weren't going to go and redo all the math in the opposite direction. This math still gives good results. You just have to remember that it's electrons that are making this math happen. As late as like 1900, people still thought that electrons were at the center of an atom and that protons were the things that moved. Like, our understanding of what is going on in an atom is very new, you know, like 100 years old. Any other questions? Okay, SI units for capacitance. That's, you can think of that as like how strong, how good the performance is of a capacitor. Are farads, named after a scientist named Faraday, and you abbreviate it with a capital F. To store charge in a capacitor, hook one side of the capacitor, let me say it this way, sorry, hook each side of the capacitor to one terminal of a battery. And so you end up with, if you have a battery here that has a voltage of V, and say this is the positive terminal and this is the negative terminal. When it's fully charged, when the capacitor is, so when the capacitor is empty, neutral, there's no charge, you know, there's the same charge on each side. Then you hook it up to the battery, and you can think of positive current flows over here, and little by little, the charge builds up on the positive side. Little by little, the negative charge builds up on the negative side. And you end up with a charge of plus Q on the positive side and a charge of minus Q on the negative side. And you also end up with a potential difference here that's equal to the voltage of the battery. So when fully charged, the voltage across the capacitor is equal to the voltage of the battery. Then, here's our first equation for a capacitor. The charge stored in the capacitor is related to the voltage across the capacitor by the equation Q is equal to CV. And this C is the capacitance. You can think of that as like the size of the capacitor. You pay more money for a capacitor with higher capacitance. So this law, you can think of, in order to kind of intuitively understand this equation, Think of this in terms of nerds stuffed in a phone booth. Okay, so in that case, think of Q equals the size of the football player. C equals the size of the phone booth. And, I have this backwards. This Q, replace that Q with V. So V is like the size of the football player. C is the size of the phone booth, and Q is the number of nerds. So here's the football player. He should have a mullet. And then, so this is the phone booth, and then in here are the nerds. No, they're not happy. No, that's his chin. Oh. They're sad. That one's pressed up against the wall. Okay. So, okay, so yeah, so he's the voltage, right? This is the voltage. The phone booth is the capacitance. So how many nerds can he fit in the phone booth? Well, it depends on two things. If the phone booth is huge, then the football player doesn't have to be very strong, right? To get, say you want to get 100 nerds in a phone booth. So the football players are up late at night, like plotting how to get 100 nerds in a phone booth. And if the phone booth is the size of this room, then the football player doesn't have to be very strong. The kicker could do it. He just has to tell them to go in. Like, go in or I'm going to get the big football players, you know? But if the phone booth is little, then to get 100 nerds in it, you need the biggest football player, this guy. Okay? So that's the relationship here. Any capacitor, in theory, you could get as much charge as you want in it. But the voltage required to force that charge in, like the size of the battery you need to get that charge in, gets bigger and bigger as the capacitance goes down, just like the phone booth. Okay? So think about this picture when you think about this equation. I'm going to draw him with a mullet next season too. Number 6. In practice, capacitors aren't manufactured flat the way I drew it. And the reason is you get more capacitance as this area, the surface area of these things gets bigger. So to get a really big, to get a high capacitance, you just have to have these enormous plates, and you wouldn't, it would just be so cumbersome to deal with. So instead, they're manufactured, you can think of them as being these enormous plates, and then they're rolled up tightly. So they end up looking, if you look at them from the side, like a, you know, wrap sandwich. Yeah. Yeah, and so when you buy them, they look like this, with one terminal here, and this cylinder is really just two plates wrapped together. And that's just so they take up less space, they're easier to transport, that kind of thing.
Do they make them like in like electronic devices and stuff like
Yeah,
that?
they're super important in any kind of electronic device.
I always see you open up like a chip, like a
Yeah, right.
small.
Yeah, right. And you see these all over the place. Yeah. I think in electronics, mainly what they're doing is switching. So the voltage that comes out of sockets is alternating. It's 60 times a second. It's going from the positive side being on the left to the positive side being on the right. And capacitors are used. But then the devices themselves want the positive side to always be positive and the negative to always be negative. And so the capacitors are used to take that alternating current and switch it to a direct current that then the electronics can use. It makes you wonder why they have it alternating current. And actually the reason, and it's pretty cool, is that you lose a lot less electricity as it travels over a large distance with alternating current, because that alternating current produces electromagnetic waves that continually like re-strengthen the signal. And so again, it's alternating electromagnetic waves to the rescue. That's the reason that we can produce electric power far away and transport it.
So kind of like your nerves do electric pulses, like going back and forth, they do alternate.
Well, it's different than that. I mean, they alternate as a way of showing, a way of changing signals. This isn't doing it to generate a signal, to send a signal. It's doing it as a way to keep the electric power strong, even as it is transported long distances. Like in your nervous system, the electric signals don't have to travel very far. But, well, let's not go into that. But yeah. Capacitance is a big, or let me say, a farad is a pretty large unit of capacitance. Most useful capacitors sold are on the order of 10 to the minus 6 farads, or even 10 to the minus 9 farads. They do make farads like over 1 farad, but those are extremely big capacitors. There's one more equation for capacitors, and that is a way to calculate how much energy is stored in a capacitor. And the potential energy stored in the capacitor is equal to, you can do this calculation 3 different ways depending on what you know about the capacitor. 1/2 times Q times V, or 1/2 times C times V squared, or 1/2 times Q squared over C. These are all the same thing. And so if you happen to know the capacitance and the voltage, you use this middle calculation. If you happen to know the charge and the voltage, you use this first calculation. All right, so let's do an example problem. So say we have a 0.1 farad capacitor. Charged to a potential difference of 50 volts. First, how many electrons, or let's say how about this? Think of it as like how many electrons have been moved from the positive side to the negative side. Second, if this charged capacitor is then allowed to completely discharge, in 1 second, what's the average current? And you'd calculate that as the change in Q over the change in time. And then third, how much electrical energy is stored in the capacitor when it's charged? Anybody have an idea about how to figure out how many electrons have been moved? Well, think of it this way. How much negative charge has been moved from, like what if the question was how much negative charge has been moved from the positive to the negative? Okay, the answer to that is Q. And so we're going to use the equation to calculate Q. And then once we know how much charge has moved from the positive to the negative, then we just have to divide by the charge of a single electron. Any questions about that? Does that make sense? So the Q that we're talking about here is, the meaning of that Q is how much so basically you're taking Q worth of electrons and taking it from the positive side over to the negative side. Okay, so we just have to calculate Q and then divide by the charge of an electron. So we use the football law. The voltage is 50 volts. The capacitance is 0.1. And so the charge is 5 coulombs. And so that means that negative 5 coulombs of charge has been transferred from the positive side to the negative side. Anybody have a question so help me clarify what's going on here? Well, if you accept that negative 5 coulombs has gone from the positive side to the negative side, now we just have to divide by the charge of an electron to figure out how many electrons make up a charge of negative 5 coulombs. So negative 5 coulombs divided by negative 1.602 times 10 to the minus 19 coulombs gives you 3.125 times 10 to the positive 19 electrons. Well, so if you if you had a truck that had 1.5 tons of apples in it, and you wanted to calculate how many apples were in it, you'd figure out the weight of one apple, and then you'd divide 1.5 tons by the weight of one apple, and that would tell you how many. That's the same thing I'm doing here. Okay, so now for part B, to calculate the current, we know that the charge is 5 coulombs. We can think of that as like the initial charge, right? The final charge, after it completely discharges, what's it going to be? 0, yep. And so the current, and this is just an average current, but it's going to be equal to the change in charge over the change in time. The change in charge is 0 minus 5. The change in time, we're allowing it to discharge over a time of 1 second, so. And you get a current of negative 5 coulombs per second. And we'll talk about this more next, but that's equal to negative 5 amps. So that's a lot of current. Oh, yeah, that's, for some reason we represent current with I, so that's the current. The amount of current that starts to be dangerous going through like your body, going through your chest really, because the danger in electric shock, besides bad burns, is messing up the electrical rhythming of your heart, you know? And so the big danger of an electric shock killing you is an electric current going through your heart. And that danger starts to appear when the current going through your chest gets up to about 1/10 of an amp. So 0.1 amps. So this is a current of 5 amps. So that's a pretty big current. So we're talking about a pretty big capacitor charged with a pretty big voltage, 50 volts. That's more than any battery we use. You know, question?
So the negative in front of the 5, that just indicates a direction.
That's right. That's a direction. That's right. So the direction, this is a direction. We don't care about this yet.
So if it was positive 5, it would just be like, it would be the same amount. It would just be a direction.
Yes, that's right. It would just be leaving the other side, going towards the other side. Okay, so we have a pretty big capacitor charged at a pretty big voltage. You see the effect of that in the current it can produce. For, in electrical terms, a second is a pretty long time. Actually, it doesn't seem like that long. But so you would think that the energy stored in this capacitor would be pretty big, right? I mean, the two things that contribute to how much electrical energy is stored in a capacitor are both fairly big compared to electrical components we're used to. So let's calculate the stored potential energy. We expect the potential energy to be big. Because Q is big and C is big. The potential energy is equal to, let's charge it or calculate it as 1/2 times the capacitance times the voltage squared. So that's 1/2 times 0.1 times 50 squared. 50 squared is 2,500. 2,500 times 0.1 is 250. Divided by 2 gives an energy of 125 joules.
Can we use the first equation?
Yep. You'd get the same thing. So, so I want you to just notice that that is compared to the energies we've been talking about for the last several weeks, that's a tiny amount of energy. Like a single food calorie is, what did I say? 4,186 joules. This is like 1/40th of a food calorie stored in that capacitor. And so I just want you to notice that the energy amounts that we're going to deal with electricity are going to always be small compared to the thermal energies that we're used to talking about. And that is really, like, in a sort of general, vague way, that's why when you plug in space heaters and hair dryers, they short out the electrical system in your house. When you use electricity to produce thermal effects, you're putting a big demand on electrical systems. Okay. Any questions? Okay, that's it.